today we're going to be talking about unsupervised image classification versus supervised. So unsupervised is the spectral variance displayed by the features in the image, and it's partitioned into a specified number of spectral classes without using prior knowledge of the area of the existing cover types or their spectral properties. And then supervised is the analyst previously identifies certain pure examples of each target land cover, and then they use that to delineate on the ground and identify in the image these cover types. So very different classification techniques, and today we're going to be talking about the first, which is unsupervised classification. So the basic elements of unsupervised classification can be illustrated using the table to the right. And so these are Landsat MSS digital values for February. And there's 4 bands on the left, and each row has a different value, different pixel value. And so then these values are plotted on simple diagrams constructed using brightness of the 2 spectral bands as orthogonal axes. And so you can see that in the middle image on the right, this 2-dimensional scatter diagram illustrating the grouping of pixels within multispectral data space. So it groups these pixels with similar values, and those groupings are what we call clusters. So these 2-dimensional plots illustrate principles that can be extended to include additional variables. An example given to analyze Landsat ETM bands 1 to 5 simultaneously. The additional variables create 3 or 4-dimensional plots of points in multidimensional data space. So this is difficult to picture, but it would look like a swarm of points with depth in several dimensions. The spectral classes of bands may sometimes correspond directly to informational categories. So that's when it's very distinct boundaries of maybe what you're looking at. So if it's like water against a dark forest of the same age, same species, maybe with the unsupervised classification, it can group those pixel values very easily because it's very distinct. And so, for example, in this figure from our textbook, the pixels that compose the group closest to the origin corresponding to open water, those are all going to be within that same cluster. But this identification is more or less obvious from the spectral properties of the class, but there's sometimes when this isn't as obvious. So seldom does that happen where we depend on such clear distinctions. It's almost like more rare. And other times, spectral classes do not match directly to informational classes, right? So the analyst would then have to come in and kind of reclassify those areas. So for example, a forested patch, they're scattered in small areas against a more extensive background of grassland. And then if these forested areas are small relative to the spatial resolution of the sensor, then the overall spectral response for such an area will differ from either forest or grassland due to the effect of mixed pixels on the spectral response. So it's not always black or white, right? There's some overlap, like you could see in this diagram in the bottom left. So in the image on the right, this is the question that we ask ourselves. Should pixel C be grouped with A or B? This question can be answered by finding the distance between pairs of pixels. So if distance A and C is greater than distance between B and C, then B and C are said to belong to the same group. And that's basically what the unsupervised classification does. And then A may be defined as a member of just a separate group. So Euclidean distance between A and B is equal to 40.45 distance units. This value in itself has little significance, right? It's like, okay, that's great that we know the distance. But in relation to other distances, in other pixel relationships, it forms a means of defining similarities between pixels. So for example, if we distance AB equals 40.45 distance units, AC equals 86.34 distance units, then we know that pixel A is closer to B than it is to C, and that we should form a group of A and B rather than A and C. And so unsupervised classification proceeds by making thousands of distance calculations as a means of determining similarities for the many pixels and groups within an image. A lot of this will make more sense as we do our lab this week, but I think it's important to know the fundamental concept behind what you're doing in ArcGIS Pro, right? So when we go through the wizard and perform the unsupervised classification, you'll know that it's doing these calculations behind the scenes. Okay, the amoeba classification. So this is an automated mapping of orthogonal empirical basis algorithm that uses more than solely spectral information. So in the previous examples, we were looking at spectral information, these pixel values, right? But this classification operator, commonly used in remote sensing for image analysis and classification tasks, goes beyond just the spectral information. It actually uses morphological characteristics. So the useful variation on the basic strategy for unsupervised classification was developed into this amoeba classification by Bryant in 1979. So here's a simplified explanation suitable for what we're doing this week. Oops. And that's input imagery, and then the amoeba classification next step would be morphological preprocessing. So extracting meaningful patterns. This step helps in capturing the most significant variability in the spectral data while reducing redundancy. So morphological preprocessing indicates the initial processing step where morphological operations like erosion, dilation, opening, and closing are applied to enhance features and prepare the image for segmentation. And I'm actually going to go back a slide because I realized I didn't really talk about this lower right example. So amoeba, as it considers classification of 3 pixels, does exactly this. So it looks at, okay, the center number, and then the center pixel differs from its neighbors, but due to its position within a background of darker but homogeneous pixels, it would be classified with the darker pixels. So in all situations, the classification assignment is based on values at locations adjacent to the sample pixel. So it's using the location of these pixels and how close they are to other pixel values. And then, so it's using more than just the distinct number of each pixel. It's actually using how and it changes and where. Okay, so this is the workflow for unsupervised classification. The first step is to configure. So indicate which classification method to use. You can also specify the output folder and the classification schema during this. And then after you configure, the next step is to train the classifier. So define the number of classes and other parameters. In this step, you define the number of classes. So what kind of categories do you want to have? How many land cover types are there? Those types of parameters. And then the third step is classify raster. So that you can use the Esri classifier definition file that's given to you like during the lab that we're going to do this week. And then during that step, the Esri classifier definition file can be used to classify other spectrally similar rasters. The fourth step is merge classes. So the classes created through unsupervised pixel-based image classification are spectrally similar, but not identified. So through visual inspection, you determine which class represents which object or feature or land cover type, and then those features are merged into that same class. And then the last step is the reclass errors. So you reclassify. So this is when I talked about earlier in this lecture where you can, the analyst would need to manually look at the satellite image and the classes that have been defined, and perhaps look at a more recent aerial image and see if those categories are accurate. So you have a chance to refine the results to reclassify any incorrectly identified classes before you export the finished classification. So there is a manual element to this classification. Okay, that leads me to our last slide, and that is gonna introduce this week's lab. So imagine if you are a GIS analyst for your local county, and you are asked to determine how many urban developments have increased in the last 4 years. So to accomplish this task, you have been given the 2001 NLCD thematic raster for your study area and the latest Landsat 8 data. So you will classify the Landsat data according to the MRLC developed class and then compare it to NLCD data. And the goal here is to create a thematic raster using unsupervised pixel-based image classification. So go ahead and watch the lab tutorial, which is on the homepage for week 14. And you can perform the lab alongside watching me do it in the lab tutorial, or you can watch it and then try to do it yourself. Good luck. See you later.